All right, here we go. Hey, Minute to Friday. Homework. All right, so the topic of today is called ratio of areas or ratios of areas. The actual point is pretty straightforward. I'll just say the example that I use to teach it is much more challenging than the concept. So I want you to focus primarily on the concept. I'll try to make it totally clear. If you get a little bit lost on the example, well, it is a challenging example. All right, so here we go. Ratios. Remember, that's just a comparison of two numbers or two values using division. We're speaking of a fraction. So A compared to B or A divided by B, the comparison is always division. Remember, ratios can also be written in colon form, A to B. We're going to see both of those today. So today we're going to do ratios of areas. So it's going to be a fraction that involves areas. So imagine this. Say I have a triangle, and from one of the vertices, I drop an altitude or a height. Then it looks like I'm connecting that segment right there to the middle. I'm not claiming that, although I might be in this case. I'm just making a connection between that same vertice that the height attaches to down to its opposite side. Okay. All right, so that's this picture right here. Notice it breaks the larger triangle up into a green triangle and an orange triangle. For both of them, I'm saying if I call the bottom the base of the green triangle is A, and the base of the orange triangle is B. And I just want you to notice that both of them share the same height. So this is two triangles who share the same heights. So I want now you consider what is the ratio of the areas of two triangles of equal heights. Okay, so ratio means fraction. For fraction means I need a number on the top and the bottom, and it says a ratio of areas. So I'm going to have an area on the top of one of the triangles over the area of the other triangle. So that's what ratio means, fraction, areas. You have to be told whether you do green to orange or orange to green. Not because I have to, I'm going to do green to orange. So the area of the green would be base times height divided by 2. And for the green one, notice the base is A and the height is H. So the area is AH over 2. Area of the orange one, the base is B, height, still height. Remember, both triangles have the same height divided by 2. So if I do a ratio of green to orange, that would be the green fraction over the orange fraction, a big ugly fraction right here. But if you remember, when you have a fraction over fraction, that's a fraction divided by a fraction. We can do a copy dot flip. We can rewrite the first fraction times the second or the bottom fraction reciprocal or flipped, right? Notice the 2's would cancel. Notice the h's would cancel, and we would be left with a over b. Now, that's interesting because a over b are the bases of the two triangles that we used. So the conclusion here is the ratio of ratio of areas of two triangles of equal height is the ratio of their bases. Okay, so base 1 over base 2. All right, so what just happened? We made that construction right there. We have two triangles of equal heights. And so if two triangles have equal heights, then the ratio of their areas is equal to the ratio of their bases. Eventually, we're going to write all this down, but for right now, that's point number 1. Okay, ratio of the area is equal to ratio, or is the ratio of their bases. Different construction. Start with a triangle. And this time, I'm going to, inside that triangle, make another triangle. And notice they clearly do not have the same heights. However, they do share the same bases. I have problems with these two colors, but I got a light color and a dark color there. So the light color has a height of H, but a base of B. And the darker colored triangle right there has a base of B, but a height of K. So two triangles that share the same bases. Same drill as the other one. What is the ratio of their areas? And this time it's going to be of equal bases instead of equal heights. Okay, so ratio of the areas, once again, I have to say, what color to what color. So we're going to do the light blue to the dark blue, if those colors look blue to you. Okay, so I need to do the area of the light blue. That would be base times height divided by 2. That would be area triangle ABC. And then the triangle inside of it is ADC, and that would be base times height. So that would be B times K divided by 2. Same drill. You can kind of see where this is going. when I do the ratio of the areas of equal bases and then do a copy dot flip again, notice the 2's cancel, and this time the b's cancel, and we're left with probably, as you would suspect, a ratio or the ratio of their heights. So if two triangles share common bases, then the ratio of their areas will be the ratio of their heights. Okay, like I said, we're going to write this all down in just a second. So if they share common bases, then the ratio of the areas is the ratio of their heights. Okay, one more. Oh, a quick pause. What do we do? Put these two ideas, state them again. If the triangles share the same heights, then the ratio will be the ratio of their bases. If they share the same base, then it'll be the ratio of their heights. All right. Next one. Imagine this. I have two triangles that clearly share nothing. But let's just say that the two triangles are similar. And then I'm going to do the same thing. So what is the ratio of their areas of two similar triangles? They don't share common bases. They don't share common heights. Okay, so ratio of the small triangle to the big one. So the area of the small triangle is base times height divided by 2. The area of the big one is E times K. It's still base times height, but that would be E times K divided by 2. Throw that into our ratio. Do our copy dot flip. We're sure expecting something to cancel. Well, the 2's cancels, and it appears that nothing else cancels. I'm left with that big ugly mess right there, but hold on, okay? For similar triangles, remember, similar triangles, their sides are in a proportion. So for instance, if I set up a proportion of their heights, so little triangle, big triangle, so the ratio of their heights, h over k, that would have to equal b over e because the two triangles are similar. That was one of the two consequences of similar triangles. They have similar triangles. All their corresponding angles are congruent, and their sides or the dimensions are form a proportion. Okay, great statement, but what am I going to do with that? Well, check this one out, right? This was what we got, the ratio of their areas. This is what we said, previous one, right? Oh, where's my pen? Sometimes this takes, there we go. There's my pen. So we're going to take this statement right here, that if I see h over k, I can write b over e or vice versa. Well, check this out. I can see that in the next slide. So there's my normal proportion. If I split that fraction as b over e times h over k, that would be the same proportion or same ratio, sorry. And in the previous statement for similar triangles, we just said that. So if I see an h over k, I can write b over e. And look, I see an h over k, so I can write b over e. And if I write that or do a substitution, I get b over e times b over e, which is b squared over e squared. So what just happened? If you have two triangles that are similar, then the ratio of their areas will be equal to the ratio of their bases squared. B is the base of the small triangle. E is the base of the big triangle. So we have their bases squared. Yay. Hey, we can write that further as that's what their scale factor. Remember, for similar triangles, scale factor is any two corresponding dimensions or sides uh, um, written as a fraction. And so therefore, scale factor would be, for instance, base over base. And we just found out that the ratio of the areas for similar triangles will be the scale factor squared, or base 1 over base 2 squared. And that would have worked for any of the dimensions. Height over height, corresponding side over corresponding side squared. That would always work. All right. So if two triangles are similar, then the ratio of the areas is the square of their scale factor. All right. And I did make that statement right there. It's not just their bases. It can apply to any two corresponding parts. So we could have done that for their heights. The height, h over k would be the scale factor. 2b over e would be the scale factor. Okay. All right, cool. So now let's write all this down. Remember, you can pause. I'm going to show you all three of the things that we just proved. And by the way, we did prove them. And then I would suggest you hit pause because I'm going to pause, take a little drink here for a second, and then I'm going to continue to talk. All right. So that's a lot. Same heights, the bases, it's the ratio of their bases, same bases, ratio of their height, similar triangles, then scale factor squared. All right, so what do we do with this? We can solve some ratio problems. I'm going to apologize up front. These are challenging problems. As long as you understood that basic concept, you'll actually find the homework a little bit easier than this particular example. So I'm going to show you 3 confusing problems in one picture. So there's the picture. This is the example from the book. And it's going to ask you to do a couple ratios. So the first picture here, or the first thing I'm going to ask you is, what is the ratio of the areas of triangles COD, O, and AOB? So I would identify those 2 triangles first. So triangle COD is that triangle. Triangle AOB is this one. So remember, we have 3 things. Those triangles are either same bases, same heights, or they're similar triangles. If not any one of those, then we can't really do anything. Well, clearly they don't share the same base. Hopefully you can see that they don't share the same height. So process of elimination, I hope they're similar. Well, check it out. We're already got that angle, let's see, DCO and angle BAO are congruent. That's the little congruence marks. And hopefully you see vertical angles. So therefore, by the angle-angle theorem, that the 2 triangles are similar. So I have similar triangles, therefore, because you see the 2 vertical triangles there, or vertical angles, I said triangles. Therefore, by AA similarity, the 2 triangles are similar. So for similar triangles, it's just their scale factor squared. All right, so now you just simply need to be, remember, we're going from the orange or whatever those colors are, from the top to the bottom or the bottom to the top. So as I read the question, the ratio of the areas COD to AOB, I'm saying that's the top triangle to the bottom triangle. So I simply, hey, pick a dimension there. Notice the only 2 corresponding parts that have numbers there are the top and the bottom. So top triangle to bottom triangle will be 3/5, right? And we're supposed to square that. The scale factor is 3/5. We square it, that's 9/25. Now, hopefully you got that one. That one wasn't too bad. The other 2 end up being a little bad. All right. So now it says, it looks like the same question, except it's different triangles. It's the same picture, by the way. So what's the ratio of COD? Well, we know COD was the top, to AOD. Now, AOD is this triangle right here. And notice those 2 triangles, once again, our 3 options are, I'm drawing it off to the side there. That's what we have. They either share same bases, they share same heights, or they're similar triangles. Notice we don't really have any markings there for angles that we could prove that the 2 triangles are similar. But in that picture that I just drew right there, you can clearly see that they share the same heights. So let's see, they share the same heights. So let's see, that's supposed to be the ratio. If their heights are the same, then it should be the ratio of their bases. So let's see, what is the base there? The base is AO and OC, and oh shoot, there's no numbers there. So this is where this problem becomes, I don't know, a little bit uglier. So this is the part where I said, eventually this problem gets challenging. All right, so we need numbers there. Well, check this out, right? I mean, we know we need to do that right there. So I need, let's see, AO over OC or CO. Well, the scale factor of the previous 2 triangles was 3/5, and I want you to notice that the 2 triangles, I'll try to annotate this, the 2 triangles, right, which you think would not be part of the top triangle at the bottom, actually share parts. Well, the first triangle is the top one, but the second triangle shares, oh, I just drew that in red. Let me do it in blue. The second triangle shares one of the sides that we just said would have the same scale factor. Well, the scale factor of the top triangle to the bottom triangle is 3/5. So that means the side that I just made in blue would be the same scale factor as, I got to pick a color that works here. Let's do green, would be the same as this side right here of the top triangle. So it would still be 3/5. So I can use that, even though it's a completely different triangle, I can use the fact that the scale factor would remain the same. So if I do that, I don't know what the values are, but I know that the scale factor is still 3/5. So if I attach an X to that value, I can at least kind of figure out what that number would be. So the base of the green triangle right there would be 5 times X, whatever that X value is, and the one of the yellow triangle would be 3 times X. And the cool thing about this is I don't even have to figure out what X is, because what we're asked to do is simply write the ratio of their bases. So that would be, let's see, the top triangle to the left triangle, that would be the yellow to the green, and that would be 3x over 5x. And you see what I'm saying here? Look, the x's cancel, so I never even had to solve for x. So the scale factor, or the ratio, is once again the scale factor as well too. That's not for all triangles, but for this one, it did work out. So this one's a way more challenging than the previous one. All right. How about one more? What's the ratio of the area of OAB to DAB? So once again, there's OAB and DAB. It's hard to see, but it's that whole big triangle there on the left all the way to B. Maybe it would help to draw it off to the side, right? Notice these absolutely do share a base, so I just need to figure out their heights. Once again, their heights, there's the heights drawn right there of the bottom triangle. Would have the same scale factor, so it would have a scale of 5, and the small triangle on the top would be 3. They used y there because we used x in the previous one. But remember, the triangle, which is DAB, is that large triangle, so its height would not be 3y, it will be 5y plus 3y. So if I now draw that, remember we're doing a OAB to DAB. So OAB is 5y, and let's see, DAB would be 8y. The y's would cancel once again, and we would get 5/8. These were challenging problems. All right, so where do we stand? Remember, same heights, ratio of their bases, same bases, ratio of their heights, and similar triangles, the scale factor squared. Lastly, this. Remember, we did prove all this. We didn't get any theorems out of this, so we end with a theorem that kind of summarizes what we wrote down. So here's a summary in theorem form of what we wrote down. If the scale factor of two similar figures, this is that last portion there, is a to b, then the ratio of their perimeters will also be a to b. We figured that out. The first one was 3 to 5. That was scale factor. Well, that was also the ratio of their areas, whether it was same heights or same bases. We still got 3 to 5 or 5 to 3, depending upon which two triangles we picked. The ratio of their areas, though, we figured out was the scale factor squared. In other words, a squared, b squared, right? That's the scale factor squared, right? So that's theorem 11.7. Go ahead and write that one down. And we finish this lesson on a kind of trumped up question right here. Imagine these were drawn on a map, so to speak, right? So you find the ratio of the perimeters and areas of two similar figures. So I'm going to claim that those two shapes are similar. We do not have any formulas for areas of those shapes, right? Very strange. But check it out. Look, there's dimensions right there. So we can get a scale factor. And so from the previous theorem says if two shapes are similar and the scale factor is a to b, then the ratio of their perimeters is also a to b, and the ratio of their areas is a squared, b squared, or their scale factor squared. So let's see, I just simply need to know whether I'm going from small to big or big to small. So if I calculate from small to big, that would be 8 over 12. That would be the scale factor. If I did big to small, that would be 12 over 8. So therefore, I know their perimeters have exactly the same scale factor. So reduce the fraction there, and that would be 2/3. And then therefore, if I do the areas, technically I'm supposed to do 8 squared over 12 squared, right? Big number. And when I reduce, I get 4/9. Well, check out what I could have done instead. You see the 4/9 right there? Look way over here, and what's 2/3 squared, right? 4/9. So before you do any of the squaring, right, reduce your scale factor and then do your squaring. Save yourself a little bit of time. All right, so hopefully that made sense. Like I said, this example is fine, but the previous example, a couple of those were a bit more challenging. As always, we get one of those table things. By the way, these are some of the problems we already did, but you'll get a table that looks something like this. I'll just do two of them for you real quick. Let's see, I'll pick, you guys always pick the high numbers as being most challenging. They're not. So if the scale factor is 2 to 3, then the ratio of their perimeters would also be 2 to 3. I'm doing this with the trackpad. This is hard to do with your finger. And the ratio of areas would be that squared. So that would be 4 to 9. I'm just squaring 2 and squaring 3. Really simple. Okay, but what if they give you the ratio of the perimeters? Well, then this would be the same, and the ratio of the areas would be 3 squared, 5 squared, or 9 to 25. No challenge there. Are the last ones challenging? Well, look, they give you the ratio of the areas, and that's supposed to be the scale factor squared. So if I take the square root of both of those, I get back to where we started. So the scale factor would be 6 to 5, because 6 squared is 36, and 5 squared is 25, and the perimeters is the same thing, 6 to 5. Well, there you go. There's how you do the table. Good luck on your homework. Do you have any questions? I saw that we talked about having a Zoom meeting next week, so I'll send you a link. I assume that you'll be okay at any time, so I'll give you a time during one of my plan sessions. Let's plan on Tuesday of doing the Zoom meeting. We'll talk about that similar polygon ones. Tuesday's good because we're reviewing for the test as well too, so we'll talk about that before we have to take the test. That will do it for today. And have a good evening, and I will see you again in class.